Everybody has.
Hi, everybody. All right. There will be a Chapter 7 Part 2 Achieve, so it will be, again, a shorter assignment. It'll be due on Monday, covering the second half of Chapter 7. Before that, so this Friday, we have our Unit Exam 2. So this will be similar to Unit Exam 1. There are 14 multiple choice and 3 short answer questions. It's not cumulative though. It'll cover content from chapters 5, 6, and 7, but 7 only through the ideal gas section, which we covered on Friday. I think that's 7.6. So 7.7, if I'm correct, which I think I am, starts Dalton's law of partial pressure. You didn't have any Achieve homeworks on Dalton's law of partial pressure for today, so that's not on the exam, just up through the ideal gas law. You are provided the same periodic table sheet. So you have PV equals nRT, you have Q equals MC delta T, and you will have delta H, the change in enthalpy of a reaction, is equal to enthalpy of formation of each product times its molar mass, sum of that, minus the sum of the enthalpy of formation of reactants times their coefficient. So all of those will be provided. You are provided R in both liters times atmosphere per mole times Kelvin, and in joule per mole times Kelvin. And you will have this conversion: 1 atmosphere is equal to 760 millimeters of mercury. Chapter 5 and 6 learning curves are available. They are due on Sunday, so in 6 days, next Sunday. They are extra credit. So remember, if you want extra credit on the next exam or the final, these are how you get that extra credit. So make sure you're completing them.
We're not going to have the curve on the 7th, right?
So I'll make it available. I guess I'll just make it available today, but it won't be due until later since all of Chapter 7 is not on the unit exam. Yes.
So will we need to know the conversions between like ATM and TOR and all of those?
So this one's provided. 1 atmosphere is 760 millimeters.
So we'll need to memorize the other ones?
Okay. So for TOR, 1 millimeter of mercury is 1 TOR. So 760 millimeters of mercury, 760 TOR. So you should remember that. And then for like the pascals, and I forgot what the other units were.
Bar.
The bar. Those will be provided. You don't have to know them. Was there a question back there? Yeah.
Just double check. Today's stuff's not on it?
Correct.
Okay, so only just having to say.
Yes. Okay, so before we continue with our notes, before we got to the ideal gas law, PV equals nRT, we covered a few different equations that relate to specific properties of a gas. So for example, we had P1V1 equals P2V2, those equations. So those are not provided, but we can generate all of those from the ideal gas law. So I'm going to show you how to do that before we move on. So here are let me find the equations. Here's the first one. P1V1 equals P2V2. So this is if you have a gas at a certain pressure and volume, and you change, for example, the pressure, So you can calculate the new value using that equation. The other one, we had V1 over T1 equals V2 over T2. And then the combined gas law, P1 times V1 over T1 equals P2 times V2 over T2. Okay, so all of these can be generated using the ideal gas law. We don't have a specific slide for this, so I'm just going to write the notes on this slide here, so you might do the same. So the ideal gas law PV equals nRT. Okay, so if we are relating pressure and volume only, so we're assuming that moles stays constant and temperature stays constant. The only thing that's changing is either the pressure or the volume. Our equation for that is P1 V1 equals P2 V2. Well, we can get that from this ideal law, or this ideal gas law equation. If moles and temperature, and of course the gas constant is staying the same, then all we have left is pressure and volume. Pressure and volume are already multiplied by each other on the same side of the equation. So we have P, now if we just put subscripts in, P1 times V1 is equal to P2 times V2. So we're just removing the remaining letters here, the NR and T, add subscripts, and we've got P1, V1, and then we do the same thing on the other side. If we want to relate volume, so this was the volume and temperature. Let's write out this equation. PV equals nRT. We are assuming that pressure remains constant, moles remains constant, and of course our gas constant remains, the same. So now we have volume and temperature on different sides of this equation. To get them on the same side, you could divide by temperature. And you'd get V1, I'll write it over here, V1 over T1. If all you're doing is this, you have V1 over T1 equals 1. But our equation that we want to use is V1 over T1 equals V2 over T2. And then the last one was pressure, volume, and temperature. So this was the combined gas law. So if all three of these are changing, we assume moles, and of course gas constant stays the same. So to have all of these variables on the same side, we divide by T, we get PV over T. And so we can use that to generate P1 V1 times T1 equals P2 V2 over T2. So this is the combined gas law, the bottom. This is the equation to relate volume and temperature if one of them is changing. And this is, the first one was the equation to relate pressure and volume if one of them is changing. So although you're not provided with these on your equation sheet, you can derive all of them from the ideal gas law equation. Okay. Questions on this? Okay, then we will continue with, where are we at? Right here. So this is our first new slide after what we covered last week.
7.7.
So this is, I think it is 7.7. Dalton's law of partial pressure. We're a few slides in. Let's go back just real quick to this slide. You don't have to, I mean, you can, but we're just going to look at this slide here. This was Dalton's law of partial pressure. This shows we have 3 containers. All of them are at a volume of 3 liters and a temperature of 273 Kelvin. Our first container has 4 moles of oxygen at a pressure of 30 atmospheres. The second has 8 moles of helium, which has a pressure of 60 atmospheres. If we combine the 8 moles of helium and the 4 moles of oxygen to the same container, same volume, same temperature, we have a total of 12 moles of gas, so 4 moles of oxygen, 8 moles of helium. And then our total pressure is 90 atmospheres, which is the sum of the pressure of oxygen and the pressure of helium. So adding the partial pressures of individual gas molecules to get the total pressure, that's Dalton's law of partial pressure. Now we can use the mole ratio, so how many moles of helium are there compared to the total amount, how many moles of oxygen there are compared to the total amount, and use that to calculate partial pressures. And so this slide is where we'll do that. So mole fractions can be used to describe the chemical composition of a mixture of gases. So a mole fraction is represented by capital X. And the A here is just symbolizing we have some gas we're saying is A, represented by A. The mole fraction of that gas A is the amount of moles of that gas divided by the total moles. So this is implying we have a mixture of moles. There's more than just gas A present. So the mole fraction is moles of A divided by total moles. And we can use mole fractions to relate the partial pressure of a component to the total pressure. So if you have total pressure of a mixture, multiply it by the mole fraction of one of the gases, that will give you the partial pressure of that gas. So we've got eye clickers. So we have 2 questions that are coming to you. Mole fraction. One is not in your slides, but the other one is, so this one's not in your slide. The second question is related to this learning check which is in your slides. And the question is not the final answer of this, but it is one of the steps that you'll have to do to get to the final answer. So I will give you some time to work on this, kind of digest what this question is asking. I'll walk around, of course, if you have some questions. Well, we'll spend a few minutes here.
So like 2 divided by 8.
Yeah.
Oh, that's the.
Because neither one of them is a full class days.
Our friends up there.
That's
If you finish the iClicker, continue working on this problem. So you're calculating total pressure, partial pressures, and mole fractions.
No, it's fine.
Oh, it's because of, so actually you're using the wrong one. That one is the voltage Kelvin. And you need the meters times atmosphere for cancel it, cancel all the
Yeah.
Spend one more minute.
Just him.
Wait, his head is the number one in the
You just did this, right? You said x 5 times 5.
Yeah.
Twice the partial pressure is greater than.
Oh, I can find it. Actually, I just don't look.
And then you multiply it by the. So you find the total pressure out, you find
All right, 30 seconds. So when that clock says 7:45 up at the top, I'm going to end it. Let me know if you
Yeah, I know, I was saying, there's 2 weeks ago.
All right, ending it here. All right, let's look at this one quickly, and then we'll go to the the other learning check. All right, in this question, we have 2 moles of chlorine. We have 6 moles of argon. So that means our total moles is 8 moles. We're asked for the mole fraction of chlorine gas, Cl2. So the mole fraction of Cl2 is 2 moles of Cl2. That's what's present. And then we have 8 moles total. So this is 1/4 or 0.25. So that will be C. Now notice we don't have units for mole fraction. So capital X doesn't have any units because we're taking moles divided by moles. So no units for mole fractions. Then this next question. So we have a diving tank. So the tank that a diver would use to breathe underwater. That is being filled with oxygen and helium. We have a 5-liter tank. So volume's not going to change. And temperature is 298 Kelvin. We are determining the total pressure of the mixture, so the total pressure of both oxygen and helium in the tank, the partial pressures of each individual gas, and then also the mole fractions of the 2 gases. So you probably started with mole fractions since that's what your iClicker was about, so we'll start there. We need to first determine how many moles of oxygen are present, how many moles of helium are present. We have 80 grams of oxygen. We use molar mass to calculate how many moles of oxygen are present. It's O2, so there are 2 oxygen atoms in every molecule, 2 oxygen moles in every mole of O2 gas, so 32.0 grams per mole. And then not a multiply sign, but an equal sign. This is equal to 2.50 moles of oxygen. So in that tank with 80 grams of O2 gas, we have 2.5 moles of O2. Do the same thing for helium. We have 20 grams of helium added. One mole of helium, 4.003 grams. So this is 5. So we have 5 moles of helium, 2.5 moles of oxygen. So our total moles is just the sum of these 2. So I'll just sum them right here. Total. .5 moles. So 80 grams of oxygen, 20 grams of helium. We have a total of 7.5 moles of gas. Now you might have taken different steps at this point. You could do a couple of different things. We'll start with finding mole fractions. So we already know moles of oxygen and total moles of helium. So we'll find mole fractions of each gas. So the mole fraction of O2 is equal to the moles of O2, so 2.50 moles, divided by total moles, 7.50. So the mole fraction for oxygen gas is 0.333. Again, no units because we're taking moles divided by moles. Do the same thing for helium. Mole fraction of helium is amount of helium, 5 moles, divided by total moles, 7.5. .667. Now, when you're working through problems like this is a good place to stop and see if your mole fractions, if you've found the mole fractions for every component in a mixture, the sum of those mole fractions should equal 1 because they're all parts of a whole. So 2.5 out of 7.5 and then 5 out of 7. So both of ours, we sum them together, we add them together, they equal 1. So we're in good shape. If you're doing a problem and you've calculated mole fraction for all components of a mixture and it's greater than or less than 1, then you've probably made some mistake. You can go back and fix that before you continue. Now, there are a couple different things that we could do and get different processes to get to the same answer. We have moles of helium. We could find the partial pressure of helium by using PV equals nRT and using just some moles of helium. That would give us the pressure of just helium. And we can do the same thing for oxygen. We have the pressure of helium, the pressure of oxygen, add them together, that will give us total pressure. Or we could find the total pressure. We know total number of moles is 7.5 moles. So if we use that for N in PV equals nRT, then the pressure that we calculate will be total pressure. Then we can find partial pressures by multiplying the total pressure by the mole fraction. Either process is fine. Both will get you to the same answer. We will find total pressure and then use the mole fraction. So our total pressure, we will calculate using PV equals nRT if we're looking for total pressure. Then we will use total number of moles, so N total times RT divided by volume. Now, the gas constant never changes. Temperature is the same for all gases present, and the volume is the same for both gases present. So 7.5 moles, total moles. We're using gas constant 0.0821 because we're working with pressure and volume in units of atmospheres and liters. So we need the gas constant that includes liters and atmospheres in its units. And then temperature is 298 Kelvin. Volume is 5.00 liters. This will give us a total pressure of 36.7 atmospheres ATM. Yes.
I'm sorry, can you just tell me how, when you use the other number for R?
Yes, so we won't use that number until later in the chapter when we're talking about energies of gases. Energy units are joules, so we will use the gas constant when we're talking about energies of gases. That other gas constant is in units of joules per mole times Kelvin. Yeah, because we haven't talked about that yet. Same question, yeah. Okay, we have total pressure. We need to find now partial pressures, and then we're done with the question. Remember, partial pressures we can calculate by multiplying the mole fraction times the total pressure. So partial pressure, I'm working kind of in the middle now. Partial pressure of O2 is the mole fraction of O2 times total pressure. So this is 0.333 times 36.7 atmospheres. And this is 12.2 ATM. That is the partial pressure of oxygen. Partial pressure of helium, again, is mole fraction of helium times total pressure. And that is 24.5 ATM. I'll give you all a second to write. I see a lot of you are still writing. Are there questions about this problem? We've got a few different steps that we're going through here. Another check you can do when you calculate your partial pressures, make sure that the sum of these equal to total pressure. Another thing you can double check. Yes.
On the test, we have to add all the units for like pressure total, pressure of test.
It's not a bad idea to do that. Yeah, it's better to include units, especially if you make a mistake. I am better able to tell your thought process and potentially add more partial credit. But if there's a bunch of numbers, I might not know what went wrong. So it's always better to include units. You should always be including units. I know you're not, but it's better to track everything. All right, we will continue on. We will push through. Next slide, we're going to section 7.8. So we'll talk about finding the molar mass or density of a gas, and we will use the ideal gas law as a tool to do that. So first, determining a gas's molar mass. So this is assuming if we don't know the molar mass, this means that we don't know what gas is present. So we'll use other information to determine the molar mass of that gas. And so we'll use the ideal gas equation, PV equals nRT. So this is ideal gas. And the mole mass relation. This is, now we know molar mass is mass divided by moles. So we rearrange this equation for it to be helpful to us in this scenario. We will have moles, N is equal to mass divided by molar mass. And this is the mole mass relation. Okay, so pressure, volume, and temperature of a gas can be used to calculate how many moles are in the sample. This is just rearranging the ideal gas law, where N is equal to PV over RT. So we've just divided both sides by gas constant times temperature to have N on its own. So moles of gas is equal to pressure times volume over gas constant times temperature. And the number of moles and the mass, so if we are provided the amount of mass and we're able to find amount of moles using the gas law, then we can use both of those values to find molar mass, where molar mass is equal to mass over moles. So we'll use all of this in the next learning check. This one, similar to your second iClicker, there is a question about this problem, but it's not the final answer for this problem. So we have an unknown gas, but look, we know the mass, 1.387. My computer was acting up earlier. It's doing it again. Okay, so we've got mass. We have an unknown sample. So we don't know the molar mass of the sample because we don't know what gas this is. It's held in a 2.00 liter. So here's our volume. It's at 1.1 atm. We've got pressure, and 310.0 Kelvin, we have temperature. We're looking for the molar mass of the gas. The first step is calculating how many moles are present. That's your iClicker. And then you'll take that and calculate molar mass. So again, once you finish the iClicker, continue working on the problem, find the molar mass of this gas. Okay. Because no matter what the gas we have pressure, we have smoke, we have volume, we have temperature.
We try our best.
You don't have to. Why did it have one?
No, it's 1.1 times 2. So with this one, just take.
I did it.
We'll say one more minute. All right, ending it here. All right, so one sec. All right, now maybe it'll work. Okay, we're good to go. All right, so we have an unknown gas. We don't know what the molar mass is. That's what we're looking for. We do have volume, pressure, and temperature. No matter what gas we have, we can use the ideal gas law, PV equals nRT. One second, friends. Just keep it like this. Okay, so we can use PV equals nRT to solve for moles. So hopefully this is what you did for that first question. PV over RT. Come on. Stay tuned. I'll be back. I'm just kidding. I'm not leaving, but I gotta exit out of this. All right, we're back. Whoa, I lost my pen. All right, I'm having a time up here. Okay, we use the ideal gas law to solve for number of moles. So PV over RT equals N. Pressure 1.10 atm times volume 2.00 liters divided by R 0.0821 liters times atmospheres over mole times Kelvin times temperature 310.0 Kelvin. So this is equal to number of moles. This is 0.08644, couple extra sig figs there. 0.08644 moles. So we have number of moles. We're provided the number of grams. So that means 1.387 grams contains 0.08644 moles. So now we use molar mass. Remember, molar mass is grams per mole. We have 1.387 grams. We have 0.08. 0. I need some water. 0.08644 moles. If you simplify this fraction, this is 16.0 grams per mole. So there is our molar mass of the gas. Yes.
Would you ever have to like identify what gas it was?
You might, but they would give you some more, like you would be given more information. Like it might be, this gas could be O2, Cl2, etc. Which one is it? Or, you know, like there are a lot of different molecules that would add up to 16.0 grams per mole. So you'd have some more guidance. All right, let's continue on if we'll make it, if I'll make it. Okay, so we can also use the gas, like the ideal gas law to find the density of a gas. Let's quiet down. We only have a few minutes left. Let's make the most of it, I guess. Okay. So the density of a gas varies with conditions. For example, we've talked about this before. If we have a balloon and we increase the temperature of the gas inside the balloon, the volume will expand. So the balloon gets larger, but you still have the same amount of gas inside that balloon. That means the same amount of gas is occupying a larger volume, so that has now decreased in density. So same amount of mass, larger volume, lower density. And so that's one example of how density of a gas will vary with conditions. We can use the ideal gas equation and the mole-mass relation that we talked about 2 slides back to obtain an equation for density of a gas. So that's what we'll do here. Now, the ideal gas equation, we'll use what we talked about on 2 slides back. So if we're looking for moles of a gas, this is pressure times volume over ideal gas constant times temperature. So I've just rearranged PV equals nRT. We also know this is the ideal gas law. We also have N is equal to mass over molar mass. So both of these equations were on the slide from 2 slides back. Now we can set the 2 expressions equal to each other. So they're both equal to N. PV over RT equals N. M over molar mass equals N. So we can say PV over RT equals mass over molar mass. Now, remember, density, which we represent as the lowercase letter rho, looks a lot like a P, but it's not. It's a Greek letter, rho. So the density of a gas remember, density in general is mass divided by volume. So M over V. Well, we can rearrange this equation to have mass divided by volume. So if we multiply both sides by molar mass, we've canceled out molar mass on the right. We have PV times molar mass. And then we just divide both sides by volume. We cancel it out on the left, and we have mass over volume on the right. Then mass over volume for a gas is equal to pressure times molar mass divided by gas constant times temperature. So the next learning check, we're calculating the density of a gas in units of grams per liter. We know what gas it is. We have temperature, we have pressure. And so this is a question that we'll do on Wednesday. We'll end here. You're welcome. But you could try it before class on Wednesday. You want to get a head start. And then don't forget, I have office hours today at 1.